My YouTube channel. I am Acho Francis Diban. Today we're going to be looking at Beer-Lambert's law. Beer-Lambert's law tried to correlate the concentration and absorption or absorbance of a system, and in the course of that he also talked about the intensity of light. For example, if we were to use a spectrophotometer, let's say a UV spec. In the UV spec, when the light leaves the source, it passes through a slit which gets into a monochromator that allow a specified wavelength of light to pass through, only specified. Then when it gets to the sample, which is the cuvette turns to absorb the radiant energy. So the intensity of absorption when it hits the sample and when it leaves the sample are not the same. So when it absorbs and it then transmits it, which will pass through down to the analyzer and the readout. So these two things are different. So at that point, we begin to look at the transmittance, which transmit the radiant energy. So if we say, for example, we are having let's call this our light source, for example, and this is how the light goes, probably through a slit. Then gets to a monochromator. This is our monochromator. Then to the cuvette. This is the cuvette. Passes through the cuvette to the what I call it, either the magnifier or a detector. Let's call it a detector. Then probably the readout. Now, if this is our cuvette, let's say we have a sample here, the intensity of light, if this cuvette tends to be blank, there is nothing in it, the intensity of light when it hits here in a blank sample is different. Let's call that one I naught. And when we fill in something here, the intensity of the transmitted is different because the sample therein must have absorbed some of the energy. So the intensity will reduce. We call that one R. In this sense, our transmittance then become the fraction of this. Transmittance could therefore become I over our I naught. This is our transmittance. Now, we also talked about the absorbance and many other stuff, which I'm going to put down. Let me be writing them here. We know that after this sense, we have absorbance, we have percentage transmittance, for example, which is equals to 100T. Percentage transmittance gives us 100 watt transmittance. Remember, transmittance is I over I naught. And also we have absorbance, which is equals to the negative log of transmittance. Then when we advance into the Beer-Lambert's law, where we have A equals to ABC, or especially say A equals to EBC. This is the absorptivity. It defines what our absorptivity. It has a special name called the epsilon, which is this. While our B here is the path length, and our C is the concentration. And many a time, A increases directly to concentration. As the absorbance increases, the concentration tends to increase in that sense. So when we plot our graph for Beer-Lambert's law, this becomes distinctive. So let me still write that one here. Let me write all the formulas up here, so that while we solve what we're solving, we can be seeing them. Okay, we have percentage transmittance, which is 100T, and we also have absorbance, okay, which is equal to our EBC. So we have two absorbance here, minus log T, percentage transmittance this, and we also have transmittance finally here, which is our I over I naught. So these are the formulas we are going to use today to explain or to make soft calculations on Beer-Lambert's law. So let's take our question, first question for example. The question says, what is the absorbance of a sample if the transmittance is 0.347? Let me list out the given. If the transmittance 0.347, am I right? Yes, 347, and they are asking us for the transmittance. What is the absorbance? Okay, this is the transmittance. What is the absorbance? Absorbance is what? This is given. So, we are looking for absorbance. Then we have to look at the various formulas associated with what? Absorbance. Absorbance here is minus log T. We also have absorbance, which is EBC. So, in these two formulas, you realize that this is the only one we can make use of because we have our T here. So, if we substitute this variable inside of here, we get what we want. So, our solution now, we say absorbance is equals to minus log T. This is minus log, our T is 0.347, and this is equals to, we'll use our calculator, we check it out. Now, minus log 0.347 give us 0.460. 0.460. This is our absorbance in the first question. Let's take the next question. Let me clean this. So, what is the absorbance of a sample? Absorbance, we don't know. That's what we're looking for. Of a sample that has percentage transmittance of 49.6%. Okay, let's look at the various formulas. They're asking us of the absorbance. We know absorbance equals to minus log T, and we also have absorbance equals to our EBC for Beer-Lambert's law. So from here, you realize that we can't move straight forward to just get our absorbance. We have to convert the percentage transmittance into what? Real transmittance. So that when we put it in here, we can get our absorbance. So first of all, let's move this. If we say that percentage transmittance is equals to 100 T, and percentage transmittance has been given to be 49.6, this is equals to 100 T. Divide both sides by 100 to get our T. This will go. So our transmittance now become 49.6 divided by 100 is equal to 0.496. 0.496. So if this is now our transmittance, now what is our absorbance? So we have to get absorbance, which they asked us initially. So absorbance now is equals to minus log of transmittance. And this is equals to minus log of the transmittance here is 0.496, 0.496. And this is equals to, I have minus log of 0.496. Give us 0.35. 0.35. 3 significant figure. That is our answer. So the question wasn't a direct question. They gave us the percentage transmitter and asked for absorbance. So we have to convert, since we know that percentage transmitter is equal to 100 transmittance. So we have to convert it to get our T. Then we bring it down here, which is minus log T. Will give us our absorbance. And that is how we proceed. Let's take a third question. So what is the percentage transmittance? Okay, now we're looking for our percentage transmittance. Percentage transmittance is equals to what? That's what they're asking us. What is the percentage transmittance if A is equals to 0 point? So I have my A equals to 0.774. So they've given me absorbance and they're asking for percentage transmittance. I can't get to percentage transmittance without knowing my transmittance. So I have to first of all get my transmittance by using this other formula, A equals to minus log T. Get my transmittance. If I get my transmittance from here, then I can get my percentage transmittance by multiplying by 100. So it's not also a direct question, but if you remember your formulas, you can always apply them. So let's see what we get. Okay, we have to get our transmittance first. So solution. Absorbance is given to be 0. Okay, let's take the formula first. Absorbance is equals to minus log of transmittance. And absorbance is given to be 0.774 is equals to minus log T. So I have to make T the subject. I divide both sides by minus. So I have log of T is equals to minus 0.774. Take it over here. Now, I'm looking for T, so I have to get the antilog of both sides. So in order to get my T, so my T is equals to the antilog of minus 0.774. And this is equals to, okay, of minus 0.774, 0.168. So this is 0.168. This is my transmittance. But what I'm looking for is percentage transmittance. So, therefore, the percentage transmittance is equals to this 100 times transmittance. And this is equals to 100 times the transmittance here is 0.168. And this is equals to 100 times 0.168, 16.8. So this is 16.8%. So the percentage transmittance here is 16.8%. Okay, let's take more questions. Let me clean this side. Okay, let's take another question. That's 3. Question number 4. It says that the measured absorbance of a solution with a path length, so the path length is given, which is B, so these are the variables given. The measured absorbance of the solution with a path length of 1.00 cm3, okay, is 0.544. That is absorbance. 0.544. If the concentration C is 1.4 times 10 raised to the power minus 3 molar, what is the molar absorptivity for the analyte? What is our epsilon? That's what we're looking for, right? Okay. Here again, you look here, you see our formula. A equals to EBC, where A is the absorbance, E the epsilon, what they are asking us, the molar absorptivity, B is the path length given, and C is the concentration. So we can use that. Solution. We say A is equals to EBC. We are looking for E, so we divide both sides by BC. BC. And our E is equals to A over BC. And this is, our absorbance is given to be 0.544. 0.544 over our path length is 1 times the concentration C is 1.4. 1.4 times 10 raised to the power minus 3. Okay, and this is equals to, so when we press the calculator, let's see what we're going to get. 0.544 divided by this, 1.4, 10 raised to the power minus 3. It's 388.5. 3 significant figure is 389. This is 389. So that becomes our molar absorptivity. Let's take another question, please. It says, what is the absorbance? Given that the absorptivity, so we are looking at A, we are looking for the absorbance. We don't know. You say, what is it? What is the absorbance? Given that the absorptivity is 2.30 times 10 raised to the power 4. The path length is B, 1.00 cm. The unit is long, per mole, blah blah blah, it's long. Okay, and the concentration is given to be 0.0000453. So they are asking us what is the absorbance. So absorbance here is equals to our EBC, which is, the epsilon is 2.30 times 10 raised to the power 4. The path length is 1.0 times the concentration. Where are we? The concentration is 0.0000453. And this is equals to 2.3 times 10 raised to the power of 4 times 0.123400453. This is 1.0419. Yeah, 1.0419. That becomes our absorbance. Let's take another question. Okay. It says that, let's clean the board first. The transmittance of a solution measured at 590 nanometer, that is the wavelength, in a 1.5 cm, that's the path length, B is 1.5 cm, cuvette was 76.2%, the transmittance. So that's percentage transmittance, that's what it means, which is 76.2%. A. What is the corresponding absorbance? A says, what is our absorbance? Okay, so we say absorbance is equals to minus log T. But we don't have T, we have percentage transmittance, so we have to convert the percentage to transmittance. But percentage transmittance is equal to 100 transmittance. If the percentage is given to be 76.2 is equal to 100 T. Then our T is equal to 76.2 over 100. This is equal to 76.2 divided by 100 is equal to 0.762. 0.762. So we've gotten our percentage transmittance, and now the A says what is our absorbance. Therefore, absorbance is equal to minus log T, which is minus log 0.762, and this is equal to minus log 0.762 is equals to 0.118. 0.118. That's A. B says if the concentration is 0. So now the other concentration here, we now have our A to be 0.118, and if the concentration is, say if the concentration is 0.0802, 0.0802. Okay. What is the absorptivity of this species at this wavelength? So the absorptivity is what we need. Remember, A is equals to EBC. We're looking for this. So our E is equals to A over BC. And this is our absorbance is 0.118, 0.118 over B, the path length is 1.5 times C, concentration is 0.0802. And this is equals to 0.118 divided by 1.5 times 0.0802. That's equal to 0.981. 0.981. That is our molar absorptivity. Let's take some more questions. Okay. Okay. It says that we should calculate the transmittance. So Transmittance is what we're looking for. The transmittance of a solution in a B is 1.00 cm. Given that the absorbance is 0.398. What addition? Okay, let's do this first. Let's say we should calculate the transmittance. There is another question. Okay, let me just read it. It said, where is it? Okay. Covariance is given to be this. What additional information, if any, will you need to calculate the molar absorptivity of this analyte? The molar absorptivity. After we're done calculating our transmittance, what additional information do we need to calculate this? So let's calculate our, is it transmittance or absorbance? Okay, transmittance. So transmittance is, we say A is equals to minus log of T. And we have absorbance. So I have my absorbance here to be 0.398. 0.398 is equals to minus log of T. Divided both sides by minus, I have minus 0.398 is equals to log of T. So log of T is equals to minus 0.398. Then my log of my T will be the antilog of minus 0.398. And T is equals to okay, let's proceed. So I have the antilog of minus 0.398. 0.3 or 0.400, approximately 0.400. This is our transmittance. They say, what additional information do we need for us to calculate our epsilon? So if you look, for us to get this, we are using that formula A equals to EBC. We have our B, which is there. We have absorbance, which is here. And C is what we need. So what additional information do we need in order to calculate, for us to calculate our molar absorptivity is C. The concentration is what we need, and it is not given. So that is the answer. Let's take another question. Okay. Our next question says, what is the molar absorptivity given that the absorbance is 0.619? Okay. The absorbance is 0.619. The path length is 1.00 cm. And the concentration is 4.23 times 10 raised to the power minus 6. Let's say, what is the molar absorptivity? This is what we done. So we just apply our formula, correct? We say A is equals to EBC. We're looking for this, so I make it the subject. This becomes A over BC. And this is equals to, my A is 0.619 over my path length is 1.0 times my concentration is 4.23 times 10 raised to the power minus 6. And this is equals to, let's see what we got. 0.619 divided by 1 times 4.23 times 10 raised to the power of minus 6 is equal to 146. Whoa, that's big. 146,335. Let me find out. 146,335.6. Let me check that out again. 0.619619 divided by 4.23 and 10 raised to the power of minus 6. 146,335.6. Okay, that's correct. That's our epsilon. Okay, let's take our question number 5. Is it 5? I've forgotten the number. Let's just go on. In each of the following, enough data are given to calculate the indicated parameters. A. Calculate A, capital A, which is absorbance, if T is 0.651. Let's clean the board. Calculate A if T is 0.6. Okay, if T is equal to 0.651, what is A? The absorbance. Absorbance is equal to the negative log of T. So this is equal to negative log of 0.651, which is equal to the negative log of 0.651, 0.186, 0.186. Okay, that's it. B, the B question says we should calculate, okay, if A is, calculate epsilon, which is molar absorptivity. If we're calculating this, if A is 0.234, B is 1.00, and C is 0.12340,391, capital N. We should calculate our E. Remember, we have A is equal to EBC and E is equal to A over BC. And this is equal to A is 0.234 over B is 1 times concentration is 0.0000391. And this is equals to, so 0.234 divided by 0.1234391 is equals to 5984.6. 5984.6. So that's that. And the last question here says calculate T if A is 0.197. It's continuation perhaps. So calculate T if A is 0.197. A is 0.197. Is that 197? So what is T? T is what? And we say A is equal to the negative log of T. So if A is this, 0.197 is equal to minus log of T. So divide both sides by minus or multiply it by minus. I have log T is equals to 0.197. T is equals to the antilog of minus 0.197. And this is equals to, okay, the second function log minus 0.197, 0.635. This is 0.635. So that's it, and that's that. So yes, where we're going to stop. The beauty about what we're dealing with today, which is the Beer's law, talks about the concentration is directly proportional to the absorbance, and in the course of that, for there to be concentration or proper absorbance, there must be what we call the absorptivity and the path length of the cuvette, perhaps, which we're going to use. So we've also talked about that. We also remember some other formulas that transmittance equals to the IL over I naught, and also percentage transmittance, which is 100 transmittance, or absorbance equals to minus log of transmittance. So when we have these formulas handy, we can easily deal with whatever we want to deal with. All these things are associated with the Beer-Lambert's law. And there are a whole lot of other questions, a whole lot of them, if we want to deal with them. But for the purpose of understanding, I believe with what we've solved so far, we can tackle any question that has to do with Beer-Lambert's law. So there is no assignment today. Just go, okay, let me give you one. It says in each of the following, enough data are given to calculate the indicated parameters. Calculate the percentage transmittance. If absorptivity is 13562, the path length D is 1.00, and concentration is 3.55 times 10 raised to the minus 6. So with this, you'll be able to come to a rational conclusion about the Beer-Lambert's law. Do not forget to subscribe and like the video when you go through it. Do have a wonderful time. Thank you.